The headline claims a nuclear-powered spacecraft could reach Saturn in just 220 days. This is the specific number you clicked for, and it is the number that changes everything. The real stakes are not the travel time itself, but the fact that this timeline destroys every existing strategy for deep space autonomy. By the end of this explanation, you will understand why the software required to survive this journey is a completely different class of engineering than what we have ever built before. Current deep space missions operate on a philosophy we can call slow robotics. A probe launched for Saturn might spend years coasting through the void, relying on ground control to make decisions that arrive with a latency of over an hour and a half. The system is designed to tolerate long pauses. It assumes that if a sensor drifts or a thruster fires slightly off axis, there is time to wait for a signal from Earth to correct it. This approach works for chemical rockets that coast for months, but it collapses entirely under the pressure of a 220-day transit window. The physics of nuclear thermal propulsion and direct fusion drive demand a shift to high dynamic autonomy, where the spacecraft must manage its own survival in real time. Consider the propulsion system itself. To achieve the delta V required for such a rapid transit, the engine must operate at extreme power levels. The theoretical studies on direct fusion drive confirm a reduction in travel time to under 2 years for robotic payloads, but the human-rated timeline of 220 days pushes the envelope further. This is not a slow burn. It is a high-energy environment where the spacecraft is constantly accelerating and decelerating. The mechanical stress of rapid thermal cycling creates a fatigue load on the hull that standard materials cannot withstand over the duration of the trip. If the structure fails, the mission ends instantly. There is no coasting phase where you can pause and wait for instructions. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This leads to the first major engineering hurdle: thermal management. In a traditional mission, thermal control is static. Radiators are sized for worst-case scenarios, and coolant flows through fixed channels. A nuclear-powered craft moving at these speeds generates heat at a rate that varies with the thrust profile. The thermal load is dynamic. The system requires software-defined thermal zoning that can dynamically reroute coolant flow in milliseconds. This capability does not exist in current deep space robotic missions. The software must anticipate thermal shock before it occurs, adjusting the flow of coolant through the reactor shielding and the engine nozzle faster than a human operator could ever react. Because of this, the navigation system faces a new failure mode. Traditional inertial guidance sensors rely on stable environments. However, a direct fusion drive produces a high-energy plasma exhaust that creates electromagnetic interference. The navigation software must dynamically recalibrate inertial guidance sensors in the presence of this plasma cloud. This is not a simple filter update. It requires a fundamental architectural pivot from radiation-hardened passive shielding to active magnetic confinement systems. The software must constantly distinguish between a sensor error caused by radiation and a real change in trajectory caused by plasma interference. Here is the thing that most analysts miss about this transition. The velocity required to achieve a 220-day Saturn transit demands propulsion control systems with millisecond-level actuation precision. This renders legacy fault tolerance patterns obsolete. We are used to systems that use triple modular redundancy with long voting cycles, where 3 computers agree on a decision before acting. In a high-dynamic environment, a voting cycle that takes seconds is a death sentence. The system must anticipate the failure before it happens. This forces us into predictive, model-based control architectures. The software must run a continuous simulation of the spacecraft's structural integrity alongside the propulsion system. It must predict thermal shock and adjust the thrust vector before the temperature spike reaches a critical point. This is a massive leap in computational complexity. It requires radiation-hardened field programmable gate arrays to handle the real-time thermal structural coupling. These are not general-purpose processors. They are specialized hardware designed to execute control loops at frequencies that current spaceflight standards consider excessive. The bottleneck now shifts from physics to people. We have the propulsion theory, we have the thermal models. But the software stack for high dynamic autonomy in such a compressed window lacks historical validation data. There are no flight records for a spacecraft that must manage its own structural integrity while under extreme thermal stress and radiation interference. This creates a critical dependency on a very specific skill set. The availability of qualified engineers who can code for both high-frequency control loops and radiation-hardened hardware constraints becomes the primary project risk. We are looking at a trade-off where the mechanical stress of rapid acceleration and deceleration demands systems that are far more complex than current benchmarks. The integration of high-power thermal management with robust, self-healing autonomous software for human-rated missions remains an unsolved systems engineering problem. The 220-day figure represents a theoretical optimum rather than an imminent operational reality. It is a target that requires a complete rethinking of how we build spacecraft autonomy. The shift from slow robotics to high dynamic autonomy introduces a critical software dependency that we have never had to solve before. We are moving from a world where we can wait for the ground to tell us what to do, to a world where the machine must decide in milliseconds whether to vent heat, adjust thrust, or reorient sensors to survive. This is not just a faster trip to Saturn, it is a fundamental change in the architecture of spaceflight itself. The hardware can be built, and the physics are sound, but the software that binds them together must be written from scratch, with no safety net of Earth-based latency to fall back on. The gap between the excitement of rapid space travel news and the lack of understanding regarding the specific mechanical and autonomy engineering hurdles is where the real work lies. We need to stop treating these missions as simply faster versions of old probes. They are a new class of machine that must think, react, and adapt at speeds that challenge our current definitions of spaceflight safety. Until we master the software for high dynamic autonomy, the 220-day timeline will remain a theoretical upper bound, a beautiful number on a page that we cannot yet make real. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.